completely reversible, but because of the way it is, and because these guys are not the aggressive, not the same aggressiveness as Grignard reagents, which are basically just negatively charged carbon, right? These guys are like, they're hanging out by a copper, and everything can bind to the copper first, and then things can shift around. Because of that, we end up with almost exclusively 1,4 addition with Gilman reagents. So Gilman-Grignard were super similar in like most of the situations we came across until now. All of a sudden, they do very different things. So, yeah, yields are going to be highest with alkyl, allylic, vinyl, aryl. What have we left out then? Oh, with primary. Okay, I was like, you've just listed all of them. Yields are going to be highest if it's primary. Cool. But yeah. So, Gilman reagents, they've got the copper. Everything gets to hang out with the copper before stuff happens. So, 1,4 addition mainly. Now, let's talk about LDA. So, if we have a strong enough base, we can get rid of the playing with equilibrium thing, which can give us some interesting results. So, let's see, do they draw us LDA? I want to say they do not. Okay, yeah, but it doesn't sort of matter. 5, we've got 40 minus 25. 15? Yeah? Thanks. Okay. I minored in math, guys. Okay, so with a strong enough base, we can take this, let's see, enolate. I mean, are we specifying that this is a nitrogen? Sure. So we can take this. Yeah. Because even if we've got this plus H, this is just 2 H's. Okay, so this is an equilibrium, right? Yes, this is going to be more favored because we don't have charge going on, and we especially don't have a positive charge on the nitrogen, so he's much happier. However, this is an equilibrium most of the time. If we get an aggressive enough base, then we can do that, and we only have this. That is going to change how reversible the rest of this basically is. So, you can use LDA, lithium diisopropylamide. Is that N diisopropyl? Oh, no, we've got with a lithium hanging out next to it, and diisopropyl is that. Yeah, doesn't matter what it is. But this is an aggressive base, LDA, that means that all we have is this. Only this, none of that, can't go back at all because this guy is, well, I mean, aggressive. So, sure, we prepare it with diisopropylamine in butyllithium, right? So we're going to use butyllithium to make this. Butyllithium, that's in the realm of like, oh, right, that's really aggressive with water, and you ruin it with water, but you ruin it really aggressively with water, and it's kind of violent, and we're in the realm of very strong, kind of violent reactions, right? Strong base, hella strong. If you use 1 molar equivalent, exactly, you can take an aldehyde or a ketone or an ester or this guy or whatever, and usually we can be in equilibrium. Take that, do that, do that. And we deprotonated. Usually this is in equilibrium, and equilibrium is generally favored that way, right? That's just how keto-enol tautomerization is. We're going to favor the ketone because, well, we love those double bonds between oxygen and carbon. But if we take this really aggressive base, suddenly we've made this, and that's a one-way reaction because we're in a hella basic environment, which is basically, the environment around this is, I took your proton and you can't have it back, bite me, right? Like, you're never getting this back, kind of a thing. So, all the way to deprotonated, or whatever else is attached to that. Yeah, aldehyde, ketone, ester, whatever, to a lithium enolate. All right, fine. Lithium enolate, whatever. So, we can do crossed enolate reactions using this, because we can take, we've done like crossed aldol reactions before, right? But like we have to choose those carefully because only one of them can have acidic hydrogens, right? Otherwise, if they both have acidic hydrogens, you get a mess of stuff. In this case, we can just pick two things that both have acidic hydrogens. I don't know, these guys. Why not? I don't know. Throw this in with a molar equivalent of LDA, and suddenly we've got this. And this is not in equilibrium. We have only this. So when we add this guy, we don't have multiple of these. We don't have any sort of room for equilibrium. This is not going back. So we've just sort of got that, and we're ready to do some attacking, right? And do some aldoling. But like this time, we're very directed. So kind of like putting one of these on here. Let's stop erasing with my hand, because, God. Wait, let's do that. There. Okay, so when we use one of these, basically this is still in equilibrium, but we're pushing the equilibrium this way so that we can do stuff here. This is a weaker base than this is. This is stronger, right? This can react with ketones and aldehydes. This guy needs an acid chloride or an acid halide or an anhydride because he's a weak base. But at least because he's a weak base, we know this is the one that got deprotonated because we stuck it like this. In this case, we can react with all sorts of stuff, ketones, aldehydes, whatever, because this guy is a strong enough base, and because we used LDA to make sure there's no going back from this. So it's kind of a way to direct this kind of thing. The proper amount of LDA, okay, so in an aldol reaction, not a crossed aldol reaction, the proper amount of LDA is going to be half an equivalent. Why? Well, because we're not doing crossed, right? So when I draw this and I say I have 1 mole of this and 1 mole of this, really what I had was I started with a mole of this and I added half a mole of LDA. And now I have each of those, right? So if I add a full mole, 1 full molar equivalent of LDA to this, and I don't add anything else in, I'm not gonna get an aldol reaction, right? Because I turned all of it into this, and now none of it looks like this, and there's nothing to attack. That's kind of the point, right? Because we can do that, and then who cares about aldol reactions? We can do crossed aldol reactions. Yeah, or enolate. I still kind of aldol, whatever. We can now do crossed enolate reactions, because if we add a whole mole of that, we get just that, and this can be whatever we want. So, and that's what they did here. What is that? C6H5, so that's what they've got up there that they're adding, right? So, we preform our enolate, and this is a very aggressive base, right? LDA, we're using, we used butyllithium, terbutylithium to make it, so like, pKa is, I don't know, high, aggressive. So we're gonna do this also in negative 78 degrees Celsius. This is gonna be acetone and dry ice bath. So it's aggressive, we cool it way down so we can just get what we want and not just, I don't know, blow everything up. And we get some of this. And then we're gonna add this to whatever we want. And I assume probably add the stuff cold and then probably just remove, maybe stir it for a little while it's cold. Maybe just sort of eventually remove the cold bath and let it slowly warm up to room temperature. That's what I would guess. Stir it for a while it's cold and then slowly warm it up. But we're gonna get our nice crossed aldol or crossed Claisen when we couldn't have otherwise done that. Because, yeah, we picked which one was going to be enolate. Okay, kinetic versus thermodynamic enolate. So we've talked about kinetic versus thermodynamic a little bit. Let's see, for ketones with 2 sets of non-equivalent alpha hydrogens is formation of an enolate anion regioselective. So, let's put that in the form of pictures and not words, because OChem is all about drawing pictures. All right, so if I have, let's just do this, really easy, that plus LDA. What am I gonna get? Well, I could get, I could deprotonate here or here. So I could get this, and I can also get that. Which one is more thermodynamically stable? That is, if we're able to reach equilibrium, which one are we going to have, A or B? B, right? More stable, more substituted. Those are pretty much equivalent. So if we let it reach equilibrium, we're going to have that. However, which one of these hydrogens is easier to get to? Is it this one? Yeah, because this is just a methyl group. It's a carbon with 3 hydrogens that are equivalent. Just going, here you go, have one of these, right? So this is probably going to get deprotonated first if we're just looking at how fast stuff goes. And we're going to get some of this. It's just that most things are very reversible, and stuff happens really fast, and we've got enough energy that it reaches equilibrium and we favor this. But now we've got LDA, and when we deprotonate, that's no longer reversible, right? We're not using a base that is strong enough to deprotonate this. We're using a base that is strong enough to keep its proton forever and ever and ever and ever and ever. So if we use, okay, there we go. I don't know why they have this on two slides, I don't like it. But if we've got a slight excess of LDA, so let's just do excess. We don't need a whole lot of excess because this stuff, we're not trying to push equilibrium. There is no equilibrium. This does what it wants. So if we have just a little bit of excess, then we use up all of this, and we end up making this guy. Why? Because this is the first one that we deprotonate, and if we have enough LDA, damn it. Sorry. This is the last thing we're doing, right? Yeah, this is just a bunch of slides explaining what I'm explaining now. If we deprotonate, we're going to deprotonate here first. If we have enough base, this is like in Gen Chem when you've got a weak acid that we're titrating with a strong base. Yes? If we reach our equilibrium point, we have no more weak acid. It's all into its, it's all turned into its conjugate base once we add just enough slight excess of the strong base, or in this case, aggressive base. But if we add not quite enough of this, then yes, we've turned most of it into this, but there's still a little bit of this left over. So this isn't exactly in equilibrium, right? The LDA got used up, but it left a little bit of this over. So now we've got some of this and some of this. There we go. A little bit of this and a whole lot of this sitting in a soup together, right? That can be reversible, right? All of a sudden, there's actually a little bit of weak acid left, and we can deprotonate either one of these we want. And there's very little of this left, but like these guys are, like which one's stronger? I mean, they're the opposite of each other. Like on the other side of this, we're just gonna have the same thing, and because this got turned into either that or this, right? This one becomes one of those guys, and this one becomes, oh yeah, the thing that one started as, right? So if we use excess LDA, we get the kinetic product, right? We deprotonate everything, there's none of this left, so there's none of this left over to mess around with trying to hit an equilibrium of this. If we don't quite hit equilibrium, then we formed a bunch of this, sure, but very quickly, these guys are gonna be like, hey, do you wanna just sort of exchange protons sometimes? And this is where we're gonna end up. Does that make sense?
Can you say one more time, like, you said if it doesn't go into equilibrium, then it just goes back?
If it doesn't, so if we add excess, let's see, if it doesn't go into equilibrium. If we add excess LDA, it can't go into equilibrium. So basically, where is it going? Like, we've taken 100% of this and turned it into this. We have 100% this in here. LDA is not going to be a, it's not going to act as a, or the protonated LDA is not going to act as an acid. acid, right? Because it takes that hydrogen and it owns it forever. So this guy is going to start looking around for, well, I'm a conjugate base. Is anybody slightly acidic? And, well, all we put in there was this and this. And we still have a little bit of this left over because we used up all of this. So, nope, nobody's slightly acidic, like anywhere in the room, right? Does that kind of? So, over here, it's like an ice table. Over here, we put some LDA and we made a bunch of this, right? But this time, it's not excess. So, we made a bunch of this, and then there's no more LDA. So we've got, let's see if I can do this as an ice table. Yeah. We're gonna do this like it's an ice table. It's gonna be fine. So, how do we start these? We have 5 of that, so 5 something. And when we do this, we get minus x and plus x on this side, right? So we get 5 minus x, we get x over here, and we get whatever this is minus x. If we make this 6, then, well, this isn't actually hitting equilibrium, right? I wrote this like an ice table, but we don't actually have to use x because we know how much is going to react, as much as possible, right? So if we have 5 of this and 6 of this, we're going to use up all of this, and we're going to have none of that left over. And we're going to use up as much of that as we can, and we're going to have some of that. And we started with none of this, and now we have a bunch of this, right? So, final, not equilibrium. There we go. Change and final. In this case, with excess LDA, we have a bunch of this and only this. Now, when we do ice tables, or, yeah, okay, when we're trying to do ice tables, right, or when we're doing titrations, you can kind of do this for the first step of the titration, that like, strong base, not reversible, whatever we end up with the final, then we put it into equilibrium, right? So now, we've got, that, oh, there we go, sorry. This, and we're trying to get this to go into equilibrium, or to go into this, so that it can go back and forth into this, right? In order to get to this guy, we have to be able to make it here. So we have 100% of this, and we need an acid. And one could call this an acid, because hey, if there's any of this left, then perfect, that's acidic. That'll react. But we don't have any of this left in this case, right? We used excess LDA, we have none of this. So this is literally this guy sitting on his own, trying to become this, and there's just, like, it can't reach this because there's no conjugate acid to, like, react with it to get there. So there's no going back. If we had a tiny bit of this still in the soup, in the stuff, so if we did, here, we'll do, for excess we have 0%, so can't move. Because this is not like general chemistry and we don't have like water to just let everybody do the proton exchanges, right? We very specifically have no product solvents or anything. So, if we do this differently, we've got 5 of that, and we have 4 LDA. Don't ask me what my units are, I don't know. Then we subtract 4, we get 1, we get 0, we get... Now, instead, say that, yeah, we can just call it just that. Sure, right? Now, we have 4 of this, 1 of this left. Yeah, whatever those units are. 4 of this and 1 of this. So now there's actually something that has like protons that can do things. Does that kind of make sense? I know I think when I did this one, we got it, and I just kind of kept going, but are we good? I just didn't want to stop halfway and make sure that, and like, get to the point where most of us were like, yeah, sure, and then like, somebody was lost and was like, nope, you've triple confused me now. All right, so basically, if we do stuff with LDA, you should be able to predict products, and you should be able to tell me which product is more favored based on how much LDA I tell you we put in there, right? Sorry, I kept going, but luckily it's just recitation.